So hi everyone. Oh wait, I need to turn this on. I think. On. Okay, I think I did a thing. So hi, welcome back from lunch. Hopefully the sun wasn't so warm that everyone falls asleep during this. I'll try and make it entertaining. So we had a lovely set of talks this morning that described to you the challenges and the ways we've overcome them in both building instruments and designing pipelines in order to observe stars and obtain radial velocity measurements of them looking for planets. So this talk is going to focus on what happens next. Namely, after your favorite observer comes to you and says, here are a bunch of data points, how do you then turn those into an actual understanding of the planet or planets that might be orbiting the star in question? So as an example of some recent RV results, these are shown here. We have a number of planets that have come out, some in single planet systems, like the work that's being done by Molly right now, some work where we found 6 planets in the system or 3. And you can see that kind of the similar characteristic of all these is that we've taken the RV data and phased it to a nice sine curve. And that's because, as Sharon mentioned this morning, if you have a planet orbiting around its star, that planet imparts a reflex motion, so it causes the star to wobble back and forth from our point of view here on Earth. And if we measure that velocity shift and plot it over time, what you get is a sine curve as the star moves away from you and then towards you and then away from you and then towards you over and over again. So in this talk, I'm going to be talking about how to take this sine curve and examine it and then extract the orbital parameters of the system. Because the 2 equations here tell you how to define the velocity of the star at any given point in time based on the parameters of a planet, multiplied by k, which is our semi-amplitude, or the height of the sine curve, and then how to turn the k measurements that we actually get from the star into the mass of the planet, assuming we know something about the period and the mass of the star. Okay. Now it's just a really quick overview. The different parameters that I'll be talking about during this are things like the period, so how long it takes the planet to go around the host star, the semi-amplitude, the velocity of that motion that's imparted by the planet on its host star, the eccentricity of the orbit, things like the longitude of periastron, or the angle where the planet goes through periapsis, its closest point of approach to the star, and the time at which that happens. The mean anomaly, which is another angular measurement of how far the planet has moved around the star, or would have if its eccentricity was 0. And then the offset, I think Sharon mentioned this morning, the idea that between when your RV template was taken and when you observe, there can be a large shift in the star's velocity, so we account for that. So to help build a little bit of intuition, let's just break down what these things do to that nice sine curve we were talking about. So here's a planet that I've created that has a period of 100 days, makes a nice sine curve like this. If we take that same planet and decrease the period to 50 days, as expected, the sine curve kind of crunches together, gets a little bit tighter. Same planet, it also has a semi-amplitude of 40 meters a second. If we increase that to 80, the amplitude of the sine curve gets bigger, okay? So just scaling factor. And then for the mean anomaly, if we change that from being 0 degrees to being 90 degrees, okay, this is a little bit harder to see, but to assist the eye, you'll note that the peak, the quadrature point of the sine curve is just shifted a quarter phase over to the left. Okay, so that's how these 3 interact. The other 2, things like eccentricity and the longitude of periastron, are a little more complex because they actually kind of get twisted together in the shape of your RV curve. So eccentricity takes you from being a nice smooth sine curve when it's 0 eccentricity or circular orbit, all the way over to this very sharply peaked form when you have a high eccentricity or a very elliptical orbit. This can actually be really challenging when you take observations, because for highly eccentric orbits, almost all of the RV motion happens over a very brief period of time. So if you studied a star that had an RV curve like this and you measured it, very carefully for months or years across this flat part, you might think there's nothing there. And then if you happen to miss these few days where it hits this spike, you would just conclude there are no planets in this system. On the other side, if you only observe during this spike, you might think it's a binary star if you didn't see the turnover point. This can be really challenging, especially with traditional telescope schedules where you might not have, these 3 days on the telescope. Okay? Now, if we convolve that then with the longitude of periastron, which, similar to the mean anomaly, takes your RV or your sine curve and shifts it in phase, so it moves it a little bit over, then you can see that we kind of go from having your sine curve in the first quarter here, the peak, to being inverted at 180 degrees. But if you have any combination of these two, you can move through this parameter space and get a large variety of different shapes to your sine curve. Okay, these are things that were, one of the challenges in deciding exactly what is reasonable when it comes to assigning eccentricities and longitudes of periastron to your data. So how then do we go from a set of RV data, which looks something like this? This is HD 69830. To something like that. This is actually a known 3-planet system made up of 3 Neptune mass planets orbiting around their star. Well, in the idealized case, what we have is a time series of data, our RV semi-amplitude measurements, and we're trying to fit to that a periodic signal, basically the period of the planets orbiting around the host star. And so one of the ways to do that is to take a Fourier transform of the time series data, because a signal that looks like a sine curve in the time domain, if you take a DFT and put it into the frequency domain, you get roughly a delta function, okay? Now, you might say this is not challenging. I could look at this sine curve and tell you what the amplitude is and what the period is, and you would be right, okay? I think most of us could try and, measure this distance and this height, and we'd feel pretty good about having parameterized that planet relatively well. Unfortunately, in real life, RV data never looks that nice, okay? This is an actual RV data set for Gliese 687. This is a nearby M dwarf. And if you tried to take the transform of this, well, it wouldn't work very well because this isn't evenly sampled. Okay? So what we do instead is do something called a lone Scargill periodogram as one option, which can handle unevenly sampled data, which is good because based on telescope allocations, you almost never have data every night for your star. And if I take the data for the star and pass it through a lone Scargill periodogram, I get something that looks like this. Okay, so now this is again, this has been transformed back into period on the bottom, but it's looking at the periodicities present in this data set. And you can see there's a very nice large peak at about 38 days. And so this actually does end up being a planet. Noted here on the dotted lines are the false alarm probabilities of 1%, 0.1, and 0.01. As Tom gave us the talk yesterday, you should not trust these to be the definitive deciding factor in whether or not it's a planet. But my personal rule of thumb is that if it's above 1%, then there's probably something periodic happening. If it's below 0.1%, it's worth looking into. Okay, so this is not me saying that's a planet, but it's, oh, it looks like there's a periodic signal in my data. I should try to figure out what's causing it, and maybe it'll be a planet. In this case, it was actually a planet. This is the first planet that I ever discovered. And so if I take that period of 38 days and I run it through my data and phase things up, then it's actually the first step to getting your RV data on a nice sine curve that you can then fit to try and understand the orbital parameters. Okay. Now another example of this is HD 141399, RV science, all about the phone numbers that are planet names. But when no one tells you, you need to just memorize all of them. So this was a data set taken, the blue points were with Keck high res, the red points are with the APF. After, what is this, 4,000 days of observing, so something like 12 years. We went through to look at what we had kind of pulled out. We said, we will take the lone Scargill periodogram, we will look for a peak. The false alarm probability there, less than 1 to the -5, so that's pretty solid. Period of 202 days. Let's make an RV curve of that, we'll twiddle with the parameters, and we get out a fit that looks pretty nice to this data. Now at this point, excellent, you found a signal, hopefully a planet. And you say, good, we'll shift that over to the left. And then you take this fit and you subtract it out of your data and you see what's left. And then there's another signal at 1100 days. So excellent, still looks pretty good, still well above that top false alarm probability line, pretty well separated, doesn't seem to be too noisy. So we fit that out, get another nice sine curve. Okay, excellent, 2 planets now. Residuals still have a planet in there. So there's another one at 94 days. Again, nice solid peak, looks pretty similar to a delta function, which suggests strong periodicity, well separated from the other ones, well above that dashed line. So we fit that out. And then we subtract all 3 of these planets and end up with one more that we're not quite sure actually. So this was presented as a possible planet in the paper. So you can see that this peak is much wider. It's not quite as well defined as the others. It doesn't quite crest that top line in the false alarm probability, so it's not as definitive a measurement. So we fit a sine curve to this. And you can actually see that the reason it's not as well established is that we've filled out this part of the curve really well, but we're kind of missing a lot of data over here. And that makes sense because the period of this thing is almost 4,000 days. So it takes a while to get back over to this part of the phase curve when we missed it the first time. Okay? So we think this is another planet. The data seems to hold pretty well with this shape, but it's presented, I think, as a candidate in this paper. And so after you fit all 4 of these out and subtracted them from the data, then finally there's nothing left in your periodigram. So now you fit all of the periodic signals. At this point, you've done kind of an individual minimization. You fit each planet as it comes out to determine things like its period and the longitude of periastron that's involved, etc. Once it's all done, you can kind of pass them through your favorite MCMC analysis to do a global self-consistent analysis, and you can then pull out the periods, the half amplitudes, the mean anomalies for all of the planets and make the triangle plots that show up in most papers nowadays. This is kind of aggressive with 4 planets in there. But then you can turn that into at least a nice little graphic. So these are the 4 planets we discovered in red. And then the dotted lines are the orbits of the solar system. This is Mercury, Venus, Earth, Mars, and Jupiter. And so this is a system of 4 kind of Uranus to Saturn mass planets that have kind of a similar structure. 3 of them orbiting close into their star and at least 1 further out. Okay? So that's kind of the brief walkthrough of how this functions. I'm now going to try and do something that's either very brave or very stupid, but possibly both, and do this in real time with you guys as a quick example. So we're going to look at HD 8574. This is a late F star that was discovered to have a planet around it in 2003. This is a real planet. I'm not going to play tricks in that regard. We're going to use something called systemic, which is one of the RV fitting tools that exist. Other options like Radvel and ExoFast2 are also wonderful, and you should check them out. But this one has an online component that's easy to demo, so I'm going to go with that until I learn how to use ExoFast2 better from Jason later today. So this is the data set for the star. Ooh, if I had a mouse, where would it be? Hey, there we go. Okay. So looking at this data set that was collected over 1,500 days, so 4 or 5 years worth of observing, you can see the RV measurements go from something like -50 to 100 meters per second. And if we take this data and pass it through, there we go, Scargill periodigram, we get a periodigram that looks something like this. Okay, so here we have this one kind of very nicely defined peak over at something like, what are we dealing with here? 200-ish days based on, yeah, read it. And it has passed all of the false alarm probability lines. So this is what we think is going to be a planet. So I'm going to, oh, this goes the other way from my laptop. I'm going to go over here and say add a planet. Maybe, there we go. Okay, and so that puts up just a starting RV curve for their base planet. I'm going to change this to be something like 230 days. Okay, so that looks a little more in line with the curvature I see here going down and then up and then down. How's the amplitude of this look? No, yeah, head shaking. Bigger, smaller? Bigger, excellent. Okay, so currently we're set to be 1 Jupiter mass. Let's just go ahead and double that to be 2. That looks better. I think a little bigger still, actually. Yeah, so like 2.2 seems reasonable. Okay. How's the alignment look? Is the peak of my RV sine curve matching with the actual data? No. Good. Okay. So we're going to take the mean anomaly. We're going to shift this by, like, let's say 90 degrees. Yeah, that's closer. Okay, I'll buy that. And again, this is just me trying to get a basic sense of what's happening in the data. And then you'll note that while these bottom parts match pretty well, I'm missing some of these upper points. So I'm going to guess that this is a little bit eccentric, that my RV curve needs to be a little more peaked as it goes up. So I'm going to take the eccentricity from 0 to be like 0.2. Okay, I'm feeling pretty good about that. How do you guys feel about this? Looks reasonable? Cool. Okay, so now we're going to say to systemic, pretty please, take all of these orbital parameters and do a nice whoop, fit to them, and now we cross our fingers. Hey, okay, it didn't change things all that much. So after the fit, where systemic has gone through and done, I think this is 11 Bergmar-Quart analysis, it's minimized the chi-squared of this, and it's spitting out that the period should be 227 days, the mass should be like 2.1 Jupiter masses, and the eccentricity is like 0.3, okay? So do me a favor and try to remember those numbers, because now we're going to come back, actually, yeah. Oh, there's, oh, chalk, yes, okay. So just out of curiosity, period, 127, mass, 2 point, what we get, 2.1? Yeah. Jupiter, eccentricity is like 0.28. Okay, so if I go back, here we go, okay, to our data, and we say, well, what was actually published for this star? That's the stellar parameters, that's their RV fit, which looks, you know, nice and similar to our RV fit. And their parameters are a period of 227 days, an eccentricity of 0.28, and a mass, here we are, of 2.1. So congratulations, you all just found a planet. Well done. Okay, so this is a simple, but like legit, this was published in 2003. This is a real planet that people took RV data of and fit out. So this is kind of the outline of how we do basic RV analyses. So for the outline, you get RVs from your favorite observer, or better yet, like go observing, go use the telescope, because that's a ton of fun. You read the RV or your RV data into some sort of analysis package like Systemic or ExoFast2 or Radvel. You look at the periodigram and the RV data. You try to identify peaks that are above your threshold and well separated from other peaks so that you don't think they're just noise in the data. You fit the data to that period. You use your software package to determine the orbital parameters using some sort of minimization. And then you look at the residuals of the periodigram to see if there are additional planets, and if so, you go back and repeat these steps, okay? So the one we did, oh, I didn't show you the residuals. There's nothing else in that system, I promise. Just the one planet. Okay, so then we need to make sure you've now identified a signal, okay? You have found a periodic signal in your data. You have figured out what the parameters of it are. Now we need to try and make sure it's a planet. And so I want to highlight a few things that you should check for when doing this kind of work, okay? So a couple of things to watch out for when fitting RV data. First, what's the difference between these two systems? Yeah, this is not a trick question. One has 2 planets. Excellent. Okay. So this guy on the right has 2 planets that are both on circular orbits, and they happen to be in a orbital resonance of 2 to 1. Okay, so the period of this guy is twice the period of the little Saturn. This one on the left has 1 planet with an eccentricity of something like 0.75. Okay. Now, to us, this is astoundingly obvious, right? Like you can look at this and say, clearly, this thing has 2 planets. It turns out that if you pass data from these 2 systems into your periodigram, it actually has a much harder time distinguishing them. And that's because the Fourier transform of an eccentric orbit shows both the peak at the true frequency, but also the harmonics, okay? So this is a planet that has a period of something like 75 days and an eccentricity of 0.75, so similar to our example on the previous page. And you, in the periodogram, get the true peak, but then also the period times 2, times 3, times 4, so all the harmonics as you go down to longer period things. Now, these small ones are probably going to get eaten up by the noise, by other kind of signals from stellar activity or rotation or star spots. But certainly the lower order harmonics, like the 2 to 1, can show up in your data. And if you're not careful, you can fit to this and say, oh, this is a 2-planet system. It's in a resonance that's really exciting, when actually it's just 1 eccentric planet. So you should always check for that. If you think you have a nice resonant chain, also try fitting for fewer planets on eccentric orbits and see if that also takes up the power of the periodigram the same way. The other thing is that window functions add periodicities to your data. So when you observe matters just as much as what you observe. These will add signals that are completely unrelated to your star. So the idea is that the time domain, again, we have this infinite sine wave idealized case that turns into a delta function in Fourier space. If you multiply that by your window function, so when you were on the telescope versus when you weren't on the telescope, that window function looks like a sinc function over here. And so if you multiply these in real time, the actual RV data will look like this. You'll get different bits of the sine curve based on when you were observing. Over here, that's going to look like a sinc function that's centered on the correct frequency, but has this spread to it, all these extra little peaks. So you could look at a periodigram like something like this and think, oh my goodness, I have found an 8-planet system. Nature, here I come, right? Unfortunately for you and science in general, this is not an 8-planet system. Rather, this is 2 planets and 1 window function being thrown into the mix, okay? So this peak and this peak are real signals. These are roughly delta functions in Fourier space caused by the planets. But then the spread that you're getting here, the other 6 peaks, are due to the way you observed, okay? An actual example of this is the PFS, so this is the Magellan schedule from this past June. And so there's an instrument on Magellan called the Planet Finder Spectrograph that I and Johanna and Sharon use a fair amount. And so the green squares show when PFS was on the telescope. And if we had a star that we were really excited about, that we wanted as much data on as possible, we would try to get it, once a night in all of these squares. Unfortunately, let's say a few of them we lost to weather or bad seeing. So these ones didn't quite happen. The window function of my observations then is a binary, okay? So there's an element for every day in this observing span, and you put a 1 if you managed to look at your star and a 0 if you didn't, okay? If I then take that array and pass it through that same kind of Scargill periodogram, what I get out is a window function that looks like this. And here you'll see a very strong 1-day peak. This is due to the fact that you can only observe once a day, mostly because, the sun gets in the way the other half. And then another peak at around 30, actually 28 days. And that's due to the fact that they don't tend to give you telescope time to look at 9th magnitude stars when the moon is down, or when the moon is new, rather. So this dark time on the telescope, as it's referred to, goes to people who want to study like 18th magnitude faint fuzzy galaxies for reasons I don't really understand. No, tons of great science in galaxies, I take it back. But yeah, it's hard to get exoplanet time when the moon is in the new phase. They won't give it to you because our targets are relatively bright. So this is why if you publish a planet that has a period either of roughly 1 day or roughly 28 days, people are going to be a little skeptical about it. And you need to do some work to convince them. Okay? Yeah, so window functions will just add things to your data. This, again, then gets convolved with any actual periodicities that come from the star itself. So you need to be able to sort that out. Okay, and the last thing, real quick, is that aliasing can make you select the wrong period. So aliasing, or an alias period, is an incorrect longer period that you see in your data due to undersampling the true period, which is much shorter, okay? So my example here, let's say you went observing for 15, well, I guess like 18 days, and you had this lovely string of RV points that you took on your star, okay? What's the period of this? Based on a curve that, goes right through all the points. What do we think? There's like a peak here and a peak here. Yeah, something like 18, 20 days, right? We see it kind of just coming off the crest all the way down to the trough and back up. I would believe that. That looks like a great fit to this data. But what's actually happening here is that we have undersampled the true planet, which looks more like that, okay? So these two curves pass through all of the same points. And to be fair, we've really just gotten very unlucky, right? Because if we had observed like right here or up here, we might have noticed this discrepancy, but we didn't. We happened to sample these points in a way that the true planet, that much shorter period object, is hidden, okay? So to avoid aliasing, you want to make sure you're, well, Nyquist sampling, or at least that you're understanding what the Nyquist sampling frequency of your data is. So the idea is that if you observe once per night, such that the frequency in your data is 1 per day, then the limiting Nyquist frequency is 2 times it, so 0.05 per day. That is to say, you can't detect any signals with frequencies longer than 2 times that S data parameter. So any parameters with periods less than 2 days. Okay. And so real quick, we're going to run through one of the most famous examples of this, which is 55 Cancri. So this is a star that as of 2002 had 3 known planets. Okay, so this is all the data that existed up to that point in red. There was a 14-day planet that had been discovered by Paul, and then there were a couple others that are on 44 and 14-year periods. Okay, so we knew about these. In 2004, Heidi MacArthur went through and added a bunch of new points using the HET telescope. And when she added this kind of high density observing span into the data and combined it with the existing points, she ran that through her periodogram and saw a peak at 2.81 days. So this is a low period. She only picked it up because those points were very dense. Okay, so this looks real good. Okay, it's a nice peak. It's again well separated from the rest of the Scargill down here. It's very tall, so this looks reasonable. They fit a sine curve to this, which looks great. and called that good. This was one of the first hot Neptunes that we discovered, 55 Cancri E. Okay? And everyone was good and happy with this for roughly 6 years. And then there's a paper in 2010 by Rebecca Dawson and Dan Fabricki that applied a new approach to aliasing analysis to the 55 Cancri data. And so they went through and studied not only the peaks in the periodic, but also the phase of these peaks. And basically their analysis says, I encourage you to go read this paper because it's actually really informative and like a study in how one should handle aliasing signals. But they said, the signal that had been previously used, that 2.8-day signal, is actually a result of like twice a day observing strategy that was used. The real signal is much shorter. Okay, it's over here, and it's more like 0.74 days. Okay. Now, a planet with a period of less than a day was mostly unheard of in 2004. I think it was unheard of in 2004. So the people that published the original data never bothered to look in that section of parameter space. It was below their sampling frequency. But by looking at that denser region and actually extending the analysis to these shorter periods, higher frequencies, they were able to find the true signal at 0.74 days. Okay? So a nice example of this is given in a paper by Mike Endel in 2012, where they went back and took some more data, which is all shown here in this like nice rainbow plot of the planets. And here you can see, so I've purposely altered this. Here's the data cut off at 1 day in period space, and you can see the 2.8-day signal standing out nice and tall. But if you slide that bar over and include periods shorter than a day, suddenly the 0.74-day signal shows up even taller. So this guy is an alias of that one. Okay? It turns out that when you shorten the period of that planet, it also makes it much more likely to transit. The probability goes up to about 1 in 3. And so when Josh Wynn went and looked at this star in 2011 after the Dawson and Fabricki paper, they found the transit, and this became the first transiting hot Neptune that we knew about, adding this really nice point to a mass radius diagram. The takeaway is to make sure you understand what periods your data are and are not sensitive to, and make sure to check for aliases when you're trying to fit planets. Okay, really fast. The other example of this is Proxima Cen B. So this was a planet where they found the signal, and then to convince everyone that it was real, they looked at all the window functions and said, this is where our planet signal is. This is where the window functions lie. So there's nothing overlapping there. These are the S indices. There's nothing there. These are the H alpha points. There's nothing there. And so since we analyzed the window function and the activity and the aliasing as well and didn't see anything overlapping, this is best explained by the presence of a planet. Okay, this is, I think, one of the more underwhelming statements of we found a really cool planet that I've ever seen. So it's a terrestrial planet around the, like, literally the closest star, and this was the way it got explained in the paper. But they did, you know, their due diligence in making sure to show everyone we thought about all these things that can look like signals, and that's not what's happening here. Okay, with that, I will say thank you so much for your attention and ask for any questions.
Thanks. Any questions for Jennifer?
Yeah, so the answer is there are different opinions. Oh, sorry. Yeah, so the question was when you're doing things like the fit I showed to 141399, where you have additional periods you think in your data, how do you handle that? Do you fit one period out at a time, or do you do a global fit? What I tend to do, and so this is a personal statement, is I start by doing the iterative fit. I find that it's more intuitive for me to be able to look at the data and identify what look like legitimate signals. And then once I've pulled out all the ones that I think are real, and I've cross-checked them against things like the window function and the activity indices that we use, any that remain, I then feed into a kind of global MCMC approach to things. So I use the iterative fit for my initial guess at the parameters and to know what signals I'm interested in. But then I do always, to get like better error estimates and such, do a globalized fit after the fact.
Any more questions? Up there, maybe?
Thanks for promoting our work on Aliasing. And I just want to say something that's a hobby horse of mine, which is the x-axis on these
Gotcha.
But what I see every single time in the observational literature is long periods.
Noted.
That messes you up.
I'm definitely guilty. I think, hell, I put it back into period space here. Like, yeah, so sorry. Next talk, I promise. Yeah. I'm in.
Do one more question. Yeah, over here. Yeah.
In the case where it was a highly eccentric one-planet model versus two and a 2-1 resonance, why would you believe the highly eccentric? Because I thought we usually don't try to believe highly eccentric planets, or we usually think they're not.
So there's nothing inherently wrong with an eccentric planet. If it's in a multi-planet system, it's much more likely to disrupt things. And so in that case, for sure, it's don't add eccentricity like just to catch that one data point that's outlying. But if the data really does seem to support it, and if you compare the results of your minimization fits or your global fits with a circular and eccentric one, and the eccentric really does seem to help without doing like funny things to grab small number of points, I think it's fine. In those, so there's a paper, I can find it and send it to you recently that did exactly this analysis and walks you through kind of how to better distinguish between the two. I think the main thing is that I think eccentric planets are still an easier or a simpler explanation than resonant chains in planets, but I think it depends on who you ask. Yeah, I can find, if you want that reference, I cannot remember it starts with a K, the first author, but I can't remember it.
Great. Thank you very much, Jen.
Thanks, everyone.